Well, welcome to the last session. They say that you save the last for best. Hopefully that is true. The grand finale. There will be fireworks. So again, my name is Martin Velez, and I'm the FinOps tech lead at Aurora, where we're building self-driving trucks and cars. And I'm going to start by asking a question. Who here has heard of Kubernetes? So pretty much everyone. Who here has heard of Aurora? Okay, a few hands. I'm happy to see that. Well, in any case, in this talk, I'm going to give you I think it's back here, but it's not. I'm going to give you a brief introduction to Aurora, what we do, why we do it. I'm going to tell you why Kubernetes is important for us. I'm going to discuss some of the challenges in doing Kubernetes Chargeback. And then I'm going to go into a deeper technical description of the approach that we built, of the approach that we took to challenge that chargeback problem. And then lastly, I'll bring up some discussion topics, and after that, we'll have some Q&A. So my goal, and I think the goal of every speaker here, is for you to listen to our talk, see where we did things right, see where we did things wrong, and how you would do it differently at your company. And so hopefully you'll take something back. I know Kubernetes is a very common, it's a very well-known topic, but it can also be a little bit mysterious and complex, especially if you don't use it. So hopefully this will at least give you a little bit of a sense. And I can assure you this is not rocket science, so it's not going to be too difficult to follow along. Well, Aurora was founded back in 2017 by Chris Urmson and a few others. So Chris Urmson was famous for winning some of the DARPA self-driving challenges. And our mission is very clear and very simple. It's to deliver the benefits of self-driving technology safely, quickly, and broadly. And we focus on safety. So every year, there are 500,000 large US truck crashes on US roads. And if you have driven in the US or pretty much anywhere in the world, I'm pretty sure you have seen an accident in your life. And tragically, people lose their lives in these accidents. So we want to make roads safer with self-driving technology. Now, at Aurora, we are partnering with truck manufacturers and car manufacturers like Volvo, Packard, Peterbilt, Toyota, and we're partnering with them to build this technology. So what we're building is something that we call the Aurora Driver. So the Aurora Driver consists of self-driving hardware, which are LiDAR, radar, cameras, and powerful custom-built computers that run our self-driving software. The self-driving software has perception capabilities, motion planning capabilities, mapping capabilities, and then on top of that, we have some off-board support, high-definition maps of US roads, and other data services. So in this video, I'm going to show you an example of what the Aurora Driver can do. This is one of our trucks driving on a highway, and our truck notices that a pedestrian is crossing the highway, which is illegal and you should never do. But it notices this about 300 meters away. It slows down, and then when the person crosses, then it resumes its journey. So this is an example of what the Aurora Driver can do. There are many, many more exciting and interesting examples. You just have to see it. So, moving on. It takes a lot of work to develop the Aurora Driver, decades and decades of work, right? And it takes a lot of computational resources like CPUs and GPUs. And if you know, I think everyone here knows this about GPUs. Number one, they're hard to get. Number two, they're expensive. And number three, we all should have invested in NVIDIA 10 years ago. We do a lot of work at Aurora, like simulations, model training, data labeling, etc. I'm going to focus on simulations because they are very computationally resource intensive. In this video, in the previous video, I showed you a log of an actual trip, of an actual truck. In this video, I'm showing you that we can take a log and we can make minor variations to the scene, like changing the time of day, the type of vehicle, the amount of traffic, the speed, and we can run the simulations on the Aurora driver to make sure that it's performing as expected and that it'll perform as expected in a wide variety of scenarios. So simulation is expensive, but it is necessary at Aurora because it helps us speed up development. Now, what our developers can do is they can write code, they can change our Aurora driver, and then they can submit this for testing under simulations, and then a report will be generated that the developer can then analyze and determine and judge if their change does indeed improve the Aurora driver. Of course, we also test on the track and we also test on the roads, but that's why we use simulation. In this video, I'm going to show you an example of a simulation. Again, our Aurora truck in a simulated environment is driving in the highway, and we simulate that there's a stalled vehicle in the lane up ahead, right? We also simulate some synthetic traffic on the left lane. And the Aurora driver sees the stalled vehicle, it sees the traffic, it slows down, and it waits for an opportunity to change lanes safely. So this is one example of a simulation, and we run millions and millions of this, testing that the Aurora driver works as expected. Now, we do a lot of work, and we use a lot of different technologies. If you were in the previous talk, they mentioned some of these technologies like Airflow. At Aurora, we have several platforms that either run directly on Kubernetes or they launch jobs on Kubernetes. And so Kubernetes at Aurora is a tech foundation. We rely on it a lot. We have close to 30 clusters. So now let's dive into, let me go back in time to 2021. So at that time, Aurora made a deal with Uber and acquired Uber ATG, which was Uber's self-driving division. So Aurora at that time was also migrating to AWS, and that's when they established the FinOps team, which is 2 of us. And one of the first things that we did is we started defining and enforcing a resource tagging policy. So we require that every AWS resource that can be tagged has a project and a contact tag. And from that, we can infer a bunch of other information. And that allowed us, as you all may know, to start having some cost reviews and start charging back data. So we would meet with leadership, with engineers, with finance, and we would talk about cost and talk about who was spending on what. The problem is that since we rely so much on Kubernetes, and Kubernetes are shared platforms, we really couldn't charge that back to teams. So there was a big chunk, I mean, these are fake numbers, but there was a really big chunk of our bill that was just like a black hole. We really didn't know. And we needed to know so that we could do budgeting, so that we could do workload optimization, so that we could do other stuff. So the topic of building versus buying has been very a common theme in this conference, right? So we also face that. So our first instinct, I don't know what your instinct is, but our instinct is to first look at our cloud provider, like AWS, and see if their native tool does what we want. Like in that case, at that time, AWS did not do anything about Kubernetes Chargeback. So then we start looking for tools. Is there anything open source that we could use to solve this problem for us? We did find a good candidate, KubeCost, but unfortunately it didn't fit in our tech stack. So we couldn't use it. And we also had a lot of expertise in-house, a lot of Kubernetes expertise, and we had people that could be dedicated to this problem. So we decided to build our own. Now, time will tell if that was the right decision, but so far, so good. Okay. Again, I say that Kubernetes could be a mysterious concept to a lot of people. And back in 2021, I also had only heard of Kubernetes. I knew that Kubernetes was used to run containers. I knew that containers are just computer processes, and that those computer processes take up CPU, GPU, memory, etc. And if you want to run more containers, you're going to need more nodes. And if you use more nodes, you're going to spend more money. Okay? So Kubernetes is not that complex once you sit down and look at it. The interesting part about Kubernetes is this control plane that you see in the diagram. And I'll highlight two components of the control plane. One is the Kube API server, which allows you to interact with Kubernetes. You can interact with Kubernetes via the command line, like the terminal, or you can interact with it programmatically through some libraries, or you can make your own REST calls. You can set up Kubernetes in your desktop. You can set it up in the data center, or you can set it up in the cloud. At Aurora, we use AWS. So for our control plane, we use Amazon EKS. And for our nodes, we use EC2 instances. Okay, so I put up this table here because some of you may want to rewatch this talk, or some people might be watching this for the first time as a recording. I will highlight two terms, pod and Kube API server. So I mentioned containers, right? Well, Kubernetes runs your containers inside something that they call pods. Now, pods can be a group of one or more containers. For the purpose of this talk, and not to complicate matters, just think of one pod runs one container. That's a pretty standard, pretty common pattern. And the other term that I'll highlight is Kube API server. Again, we're going to be talking about those two things over and over again for the rest of the talk. So just keep those in mind. So now I'll discuss why Kubernetes Chargeback is difficult. So the reason number one is that clusters are shared by different users or by different projects. This has upsides, but it also introduces a challenge that while in this diagram I'm showing you a snapshot of an EC2 instance that runs for 1 hour, and in that 1 hour, different users can launch pods that are running on the same instance. Now, Aurora gets billed for the entire hour, so we have to figure out how do we split that cost fairly amongst all the users. And if you go to FinOps.org, there's an excellent article calculating container cost. And if you get the FinOps Cloud book, or is it Cloud for FinOps? Cloud FinOps book, whatever, I forget the title. But there's also an excellent chapter there that kind of gives you a good summary of the problem. Now, reason number two, and now this is when we start getting more technical, and this is when you start, once you start playing with Kubernetes, you're going to discover that, hey, Kubernetes is great at container management, but it doesn't really store data. So Kubernetes stores data in something called etcd, and it stores it for a very short amount of times. So in this diagram at the bottom, I'm showing you a terminal, and I'm showing you that I ran a command called kubectl or kubectl, and I'm using that command to list all the pods in the infra efficiency namespace. Now, you can see that I listed 2 pods that are running, but it doesn't tell me all the pods that ran in that cluster, right? It doesn't keep that data. So that presents a challenge. And that sort of guides what we're going to do, or what we needed to do, which is to build our own database of pods. And then once we have a database of pods, then we can also try to assign a cost estimate to them. So reason number 3, and again, this kind of guides your approach, at least for Aurora, is that Kubernetes generates a lot of data. At Aurora, we have clusters that can scale to thousands of nodes, and those nodes can run millions of pods every single day. And if we want to keep track of pods, we need to be able to handle that amount of data somehow, okay? So, moving on. So I'm going to just dive in and tell you exactly what we did at a high level. And then from here, I'm going to kind of dive into more details. But at a high level, what we did is we wrote a program called Podwatcher. And what Podwatcher will do is that it will talk to the API server, and it will collect, it will watch pod events, it will extract information from those pod events, and it will persist that data into our data lake, right? And then once that data is in our data lake, then I wrote another program called Podcost, which reads this data and calculates a cost estimate for pods. So in the end, what we end up with a database of pods where every pod has a cost estimate. And that's what we want. So one of the prerequisites is that we need tagging, right? Anytime you want to do some cost estimation work, you want to tag things. So in Kubernetes, I explained that you have nodes. So what we did is we set up some processes that automatically inject labels on our node resources. And we inject things like the pricing model, the instance type, and the region. And we're going to use this information later to determine what the price of that node was, right? We'll use other APIs and other information to determine a price. Now, we also set up a tagging policy for pods. So we require that users add two labels to every pod that they launch, contact and project, which, going back to our original tagging policy, matches. And we also ask them to tell us how much resources their pods are going to require. Now, Kubernetes does not require that you do this, but this is going to be useful for us in determining what proportion of the instance cost to assign to the pod, okay? So far, I hope that everything I'm saying is pretty straightforward, because I'm trying to retell my path and my logic and my reasoning when I was building this. So now let's dive into Podwatcher a little bit more. So again, I mentioned that I want to build a database of pods, and I mentioned that I want to have cost estimates in those pods. Well, this means that I need to keep track of pods. I need to keep track of pods when they're created and when they're terminated. So that means that you need to understand the pod lifecycle. When you create a pod, the pod goes into a pending phase. And when all the containers inside a pod are running, then the pod transitions into a running phase. And when the containers have finished and they have all finished successfully, then the pod transitions into a succeeded phase. If any of the containers inside the pod fail, then the pod transitions into a failed phase. And there's also an unknown phase, but that's not super relevant. Okay, so I mentioned that I want to keep track of pods. I want to build a pod database. So this is how I can watch pod events using the command line. Again, I'm using kubectl, and I filter the output to focus on one pod, which is identified by name. And you can see the status, which is all the pod phases or the entire life cycle for the one pod. And if you look at the yellow boxes that I highlighted and you compare the times, you can see that this pod lived for an exciting life of 7 seconds, right? Some pods can live for months, but in this case, it lived for 7 seconds. And we're going to charge it for the 7 seconds because those are not free. So I'm going to give you a recipe, and it's a 3-step recipe that I followed. So it's easier than baking a cake, right? So baking a cake is much harder. So the first thing that I needed to do is, okay, I know how to watch for pod events using the CLI, but how do I do this programmatically, right? Because eventually I want to have a program that's running and that's tracking pods automatically for me. So what I needed to do was set up a client, and luckily Kubernetes provides excellent open source libraries that you can use, and it provides clients in different programming languages. And at Aurora, we use Go for this kind of stuff, so it's only natural that I wrote this in Go. And what I did is I set up a client, so if I'm developing, I'm interacting with the cluster from outside the cluster, and then when I deploy the Podwatcher is going to be running inside the cluster, and is going to be collecting information that way. Step 2 is to set up an informer. Now, this is a Kubernetes library concept. And the reason that it exists is because if you go to the official Kubernetes website, it talks about efficient detection of changes, or how to efficiently watch for pod events or node events, etc. Now, here's the naive way of doing it. Let's say you write a program that every minute tries to list all the pods in a cluster. If you do that, you're going to, especially in a large cluster with lots of pods, you're going to tax your API server, you're going to overwhelm it, and you're also going to overwhelm your own program because you'll be processing a lot of information. So instead, an informer lets you implement a list, then watch pattern. And what that means is that when you first start up Podwatcher, it's going to make a list call to the API server, and the API server is going to send me back a list of all the pods. And then the Podwatcher will cache all those pods. And then at the same time, the Podwatcher will register a watch callback. And then the API server will send only change events to the Podwatcher. So that's a more efficient pattern. Now, what do you do with those events? Well, that's step 3. So what I had to do then is to implement some event handlers. So there are 3 kinds of events. There's an add event. That's when a pod gets created. There's an update event. So that's whenever there's a change to the pod spec, like I mentioned, containers starting up or exiting, or you can actually change the pod spec on the fly. Whenever there's an update, you'll get an event like that. And also there's a delete event. So from the add event, that's when Podwatcher first seeds a pod for the first time. And from that, you can get the name, you can get the start time, you can query for the node information for that pod. When Podwatcher sees an update event, that's when it's keeping track of these transitions. Because going back to something that I mentioned is that Kubernetes is great, but it doesn't even tell you when a pod ends. So it tells you when a pod starts, it tells you when a pod gets deleted, but it doesn't tell you when it finished its work. So you need to infer that from its pod lifecycle, which I showed you a few slides back. So that's why the update events are important, because that's how you're going to figure out how long did this pod run for, okay? So putting it all together in this architecture diagram, in the purple gray looking box, you'll see Podwatcher and some of the main components. And you can see that it interacts with Amazon EKS, which is the control plane. And then it sends data to our data lake. So the data passes through API gateway, Kinesis, and it gets written to S3. Now, there's a Podwatcher in every single cluster, as I said, and they're all sending data to the same stream and the same location. And then that data, once that data is there, then we can do whatever we want with that data. So we can use our dashboarding tools. Other programs can read that data, or other users can look directly at that data. Okay, and this is what that data looks like. So you can see that this is not obviously the entire schema, but you can see that I store the cluster information, pod information, node information, and cost allocation information. Okay, so one important thing to note is that this is event data. So this is not yet your database of pods. This is just pod events that you're keeping track of. And this is going to be useful in the next step. So Podcost. Okay. So now that you have this pod data in your data lake and you've persisted it longer than an hour, right? You need to figure out how I'm going to calculate a cost estimate for every single pod. So we tried different ways, we thought of different ways of doing that, and eventually we settled on something that's pretty straightforward. So we say that the cost of a pod is the elapsed time times the instance price times the max ratio. So if you think about it, it's time times rate times usage, right? The proportion of the instance that it's taking up. So let me illustrate that with an example. So in the left, in that yellow rectangle, I try to represent an instance, and I try to represent a timeline from 1 p.m. to 3 p.m. And if you look at the bottom, you'll see pod 44, right? So pod 44 is running on 1 GPU. It requested 8 CPUs. It requested 48 gigabytes. And this is a G4DN.12x large instance, right? Now, if we try to calculate the cost, we'll see that this pod ran for 2 hours. And if we can retrieve the instance price, that's in our data set. Well, actually from APIs. And then we can also calculate the max ratio. So the max ratio is the maximum of the CPU ratio, GPU ratio, and memory ratio. So if we look at the resources, then we'll say that the CPU ratio is 8 out of 48, which is 0.1.6666. The memory ratio is 48 out of 192, which is 0.25, and the GPU ratio is 1 out of 4, which is also 0.25. So we'll say that the max ratio is 0.25. Now, if we plug in these values into our cost model, we will say then that the cost of pod 44 was $1.956. And we can do this for every single pod that's running on this instance, in every cluster, and then we can have what we want, which is a database of pods with cost estimates, with cost allocation information, et cetera. So again, putting it all together, I wrote a program called Podcost, which reads the Podwatcher data that I explained earlier, and it talks to AWS pricing APIs. It puts it all together, and it calculates the cost estimates for every single pod running in every single cluster, right? And then it writes this back to the data lake as a new data set called Podcost. And we can use big query tools like Amazon Athena to then build dashboards to make this data available to other programs or other users. I noted there that Podwatcher data is updated every 15 minutes. We run Podcost every 30 minutes, so users get the data pretty much in real time. This was important because if I'm a user and I run a job, sometimes I want to know what it costs right away, right? So this being near real time was sort of a requirement from the get-go, okay? Now this is what the Podcost data schema looked like. You'll see that it looks very similar to the Podwatcher data. You'll see that we still have cluster information, pod information, node information, cost allocation information. We have this new fields that you can see that allows us to calculate the cost. So going back to the original problem, right? At Aurora, we use Kubernetes a lot. And let's say we have a cluster that costs us $10,000 a month, right? So we couldn't charge that back to the actual users. Well, now we can. So now we have this data, and if you look, we have the cluster. So now we can, for a given cluster, for a given time period, we can actually know how much to charge every single back to people and projects. So yeah, I think yeah, I'm thinking if I've graded something. But yeah, that's it. This is sort of our data. And then once we have this data, we can also merge that back into the AWS billing data, and we can show that instead of the non-helpful original cost. So we can sort of marry that data together, but that's probably not worth discussing right now. What I will say is that we spent maybe 30 minutes talking about pods and pod cost, and no one cares about pod cost. No one really cares about how much pod 44 costs, right? No one cares about that. That's too low level. What people really care about are workloads. So in one of the earlier slides, I showed you that we used a lot of different platforms, and I said that those platforms either run directly on Kubernetes or that they launch jobs on Kubernetes. So that's what people really care about. They care about how much do simulations cost, how much does training a model cost. They care about protecting from cost overruns. So even though people don't really care about the cost of an individual pod, generally, because there are situations when they do care, this unblocked many of the higher level work, right, that I list here, like doing anomaly detection, doing CI chargeback, budgeting, right? Can you really do budgeting if half of your build is Kubernetes and is a black hole? You really can't, right? We're focused a lot on workload optimizations. We have a working group, a task force that all they do is work on, well, not all they do, but part of what they do is make some workloads more efficient. And if they can make a workload go from $200 to $100, that saves 50%, and then that workload runs every single day or multiple times a day, then that's real money. Okay? So this is the last slide of my talk. Again, I described to you how I built a Kubernetes chargeback system. I'm probably going to give you the impression that you can do it too, which you can. Again, it's not rocket science. But I'm also going to give you the warning that maybe you don't have to. For one, there's a lot of excellent vendors out there that could help you with this problem. Also, I don't know much about the other cloud providers, but I know that AWS has recently started being better about this. So they recently started supporting KubeCost, and they recently released a feature called split cost allocation. Now, I myself haven't had a chance to try the split cost allocation, but from reading the docs, it looks very similar to what I'm doing essentially. So who knows, Well, I listed a bunch of additional topics. This is there's a whole conference dedicated just to Kubernetes called KubeCon. It is a very complex and growing ecosystem, right? I only touched a small part of it. I hope that through this talk, you have a better sense, a better understanding of Kubernetes. Hopefully you got that out of it. And, Kubernetes chargeback may not be an issue for you right now. It might come up in the future. So now hopefully you have some additional knowledge that you can take back. So I guess I'll open up questions now.
Big round of applause first. Thank you so much, Martin. That was fantastic. We know containers are the new VMs, so very timely topic, important for everybody, I'm sure. I saw a lot of hands go up. Who wants to kick us off with questions?
Hello, I really like the presentation, very detailed, technical. I would like to ask about how you deal with waste, node level waste, when it's not running enough pods, so it's excess capacity in the node, or pod level waste, when the pod is requesting more resources and it's not using all of it.
That's a good question. So you're asking how do we track utilization at the pod level?
Waste. Like charges, like you are charged on the node.
Oh, okay.
And if you're not using the node fully, just partially, then you...
Oh, okay. Okay, so let me translate your question. So he's asking about overhead, cluster overhead, right? So in one of the diagrams that I showed earlier, I showed that you can have multiple pods running on the same instance, but you can have multiple pods and still have unused resources on that pod. So then who do you charge that back to? So that's the second bullet point right there. So that is a very interesting question. The way that we do it is we take that overhead and we charge it proportionally back to all the people using it. So every cost estimate gets a inflation factor charged in, and that kind of encourages people to reduce that overhead and to be more conscious about any time that they're underutilizing resources. But that's a really good question. That's a big thing that we had to address. Go ahead.
Martin, thanks so much. This has been a fantastic presentation. Two questions, very, very quick. One, at KubeCon, have you seen the emergence of a FinOps portion?
I've never been to KubeCon.
Okay, fair enough. And
but my teammates have. So my teammates have, and when they go, they always come back and they give me a debrief on what's happening. So far, they're happy with our solution. Yeah.
And the second part is, and with respect to the vendors that are out here, that's great. Podwatcher, do you have it available on GitHub?
We haven't open sourced it. That's a good question, and that could be a tool that could be open sourced. I would have to go and talk to legal, and it'll be a whole process. It is, when I was building it, I thought, why isn't there a Podwatcher already open sourced? And when I built it, I did build some Aurora specific things. I didn't make it super configurable. So for me to open source it, I would have to go and do some refactoring. I would have to talk to my manager and legal and all that. But that's a really good question. Yeah.
Hey, Martin.
Where's
Right here. Hey.
Oh, sorry. Okay.
Hey, that was fantastic. I know you worked on that for years. That had to be hard. Do you store the data time series? And if so, what are you doing? What architecture, what database are you using for your time series data?
So that's a good question. So I mentioned two data sets, right? I mentioned the Podwatcher data set, which is event data, and the Podcost data set, which is now one pod, right? So it's a record of pods and their cost estimates. We don't use time series because we have the event data with, we thought about using time series, but it wasn't really necessary. We do use time series vendors like, we use Chronosphere. Now we migrated to Grafana. So we do have time series data, time series services for metrics and logs, but not for this kind of data. Any other questions? Okay.
Thank you very much for the presentation. I noticed you call on on-demand costs, and what if like a reserve instances is covering the node? What kind of cost do you charge back eventually?
Okay, that's a good question. So I know that a lot of companies deal with reserve instances and savings plans, and then the pricing can be a little bit tougher. At Aurora, we have a different arrangement where it's a little bit easier to calculate discounts and include those. So if you did that, I think you would have to include that in your cost model somehow. But yeah, that's a really good question. I know a lot of people use those kind of pricing agreements. So. We have a different agreement. I don't want to go on it because it gets recorded, but we have a different agreement.
Hi, thank you for the presentation. I'm just wondering, what's your finance level of granularity for chargeback, and especially for the CI chargeback? Are you charging back by team or by like engineer?
So this is an interesting question. I guess it could be debated a lot, but for what we try to do is we try to charge individuals, because then we can use org tree data like Workday. We can query Workday, find out what our work tree is, and then just charge that up the organizational tree. So teams, if you really think about it, teams are just labels or names, right? So that we do that in ETLs over billing data. But for us, we really want to charge everything to an individual. So if we could do that, that helps us with cost attribution, and then if there are issues that we need to investigate, like some job is going out of hand, that we can talk to one person. But yeah, that's a good question. Great.
How close did you get to invoice reconciliation with Podcost? Were you to the penny? Were you close? Was it an iterative process? What did that look like?
So as he asked, we do have some cluster overhead. And thanks to this, we can identify or measure, get an estimate of that overhead that we're experiencing. And once we charge that, I mean, we know the pod cost, we know the true cost. So by doing this inflation or this charging back of the overhead to the users, we can just have a one-to-one replacement. So if we have a $10,000 cluster, pod cost will be $10,000. So it's like down to the pennies, pretty much. Yeah, go ahead. Oh. Guys, keep the questions coming. I think this is awesome.
Yeah. Once again, thanks for the great presentation. One of the things that you mentioned in calculating the proportion that you charge, do you use the requested or the utilized?
That's a really good question. So back when I looked at KubeCost, so KubeCost focused on using the utilization, and we cared about using the request. It's a subtle difference, but it's very important because, as I mentioned, we have platforms that launch jobs. So we have a platform that will say, I have 10 pods, and they're each requesting one CPU. Let's say 4 pods. They're requesting one CPU, right? Am I going to allocate 4 CPUs for them, or am I going to allocate 2? Like, I don't, right? You want to allocate what they request. And that's why we charge them for what they request, not for what they use. Exactly. That would make our unallocated charges even worse. But yeah.
Thanks for the presentation. It was really insightful. My question is regarding the demand ingestion process, like when we have more features coming. How predictable can you be? Like, how can you measure, or do cost analysis in regards to Kubernetes? for business?
So once the data is there in our data lake and we merge it with our normal data, if you use AWS, I'm sure you're familiar with the CUR, right? So the cost and usage report. So we merge our data with that. And then we just ran our standard anomaly detection algorithms. We have budgets on that. We can run pretty much standard analysis. I mean, pods, if you really think about it, a pod is, we get charged for the instance, and the work that we did is break it down by the pod. So then we're showing, in the bill, we're showing pods as a resource. And then it's just like normal resources. Whatever you would do with your other resources, you would do for pods. So if someone, we have an anomaly detector that is constantly watching this data, and it will alert and say, hey, in this namespace, these jobs are using an abnormal amount or costing an abnormal amount of money. So then we'll tag that person and we'll say, hey, what's happening? And normally it's like, oh, we have to retrain this big model and it costs us $20,000. Sorry, but I'm like, so that, it's just normal data. Now on that topic, someone did mention that there is a push towards standardizing container cost data. I think, I forget what they called it, but there is a push towards that. So I would be all for that. So, but that's a good question. Any other questions?
Sorry, I had to figure this out. So 2 roadmap questions. Do you plan to aggregate your data up to other Kubernetes constructs like deployments or services or namespaces or anything of that nature? And then the second question, do you plan to integrate this with Carpenter? And if so, can you kind of talk a little bit about that?
So we do use Carpenter. So Carpenter is a tool that lets you kind of resize your cluster and moves pods around to help you save money. Now, we do the aggregation on the data based on whatever dimensions we have in the data set. And usually those dimensions come from the labels, like the node labels or the pod labels. So yeah, we have, for example, we can provide cost estimates for long-running services. So if we have APIs, we'll provide compute cost estimates for that. If we have batch jobs that run for an hour or whatever, we'll provide cost estimates for that. If you have a Kubeflow pipeline that's running, we'll provide cost estimates for that. That's a cool thing about having a fundamental technology like Kubernetes and having a tool like this, that then at the higher level, you can provide cost estimates for anything that uses that. It's challenging, but it's possible. Where? Okay.
Yeah, very quick question. What is the key you use to join your podcast data with the CUR as far as EKS cluster cost is concerned?
So that's a good question. So roughly what we do is we take so we have a cluster tag on the CUR. So if in one of the tables I showed like Prado 1, so we can say the cost of Prado 1 is $10,000. So we'll basically replace that with the cluster key on the Podcost data. That's how we join them. Okay. Hopefully that makes sense.
Follow up or any other questions?
Well, thank you all.
Oh, here we go.
Lots of questions. I love it.
Hey, thank you for the presentation. Definitely one of the best ones experienced this conference. Yeah, very, very good presentation. Just quick one was, as you went through this exercise, what was kind of the outcome of it to the business and to leaders? Did you see a reduction or more efficient usage, reduction in cost, reduction in spend, reallocation of spend? Like how did that play out?
I mean, to put it plainly, this has had a huge impact to the business. So like I mentioned earlier, let's say half of our bill was Kubernetes. We had no visibility. So once you unlock that visibility, now you can do everything. Like I said, even budgeting was blocked, right? We can't really budget if we can't charge. Anomaly detection, we couldn't really track jobs. We had jobs that would cost us lots and lots and lots of money, and we didn't know that because we couldn't charge those jobs. We had people running workloads, like almost a $20,000 job every week, for example. Like we didn't know that. And then we like, hey, can you not run that often? Because now we know how much it costs. Oh, my bad. So they'll say things like that. So it's had a tremendous impact. Like I said, it's very fundamental at our organization, and it's unblocked a lot of things. So yeah, thank you.
We got another one right here.
Thank you. This is a great presentation. Just curious, do you know how much it costs to run Podcost?
I was hoping someone would ask that. So it costs like, the last time I did the math, it cost like $100 to run this whole ecosystem. I mean, Podwatcher is a very lean and mean program, so it's very efficient. Podcost is an ETL. It's a Python program that runs. I said 30 minutes. So it's a very inexpensive system. The data, now that's separate, right? If you store the data, that's going to cost you whatever that costs you. So
ROI on that one. All right, who has another question? Everyone's ready for drinks? Is that it? All right, thank you so much, Martin. Let's give him another big round of applause. That was an excellent presentation.
Thank you.
Thanks for watching. Check out more FinOps X 2024 content on our YouTube channel on the 2024 playlist. Support our channel by liking, subscribing, clicking the notification bell, and by leaving comments and questions for our speakers. We appreciate your support.